Right. Morning, everyone, or afternoon or evening or whatever happens to be in your neck of the woods. I'm Walt Magnuson. I direct the Internet 2 Technology Evaluation Center, and I'll be mainly talking about 5G here for the next 20 minutes. So 5G, LTE, actually LTE stands for long-term evolution, and the transition from 4G to 5G is a part of that transition. And there are a very, very significant number of attributes to 5G that really enable us to do work in a digital twin, in a digital twin arena. As Gian said, the reality is what we need to do here is to take information and then create a virtual twin of it. Well, in order to basically be able to create that twin, you need to have inputs from the real scene, from the real architecture, and be able to go ahead and bring it into the twin. That's basically where 5G comes in. So the major difference between 4G, 1G, 2G, 3G, and 4G is as we went through the transitions, the speed kept increasing, the capabilities kept increasing. It went from analog to digital services, started adding in voice services, et cetera. Problem was that there were different standards throughout the globe. So an organization called 3GPP came along and started to standardize and normalize the entire process. So between the International Telecommunications Union and 3GPP, the process of standardization of 4G and 5G has pretty much been complete. It's now to the point that if you buy equipment from manufacturers, manufacturer A is going to be able to interface with manufacturer B. Manufacturer B is going to be able to interface with manufacturer C. And more importantly, service provider A, let's say AT&T, connecting to service provider B, there's going to be interoperability there as well. So we've got a network now where interoperability can be built. As I said, it's an evolution, and LTE started with release 8. Right now, they're on release 16, which includes 5G standalone and brought in a number of different features and attributes. And then right now, there's in the process of transitioning over to release 17. So it's a process that will keep going on as time evolves. So what does that mean for us? The major difference between 4G and 5G is 5G brought in a number of attributes that really for the first time allow us to build our own networks within our own enterprises and organizations. 1G through 4G pretty much was owned, operated, and managed by the service providers. And if you wanted to be a part of it, you basically bought service, you bought a SIM. If you needed to connect an IoT device that connected to the 4G network, for example, Coca-Cola and Pepsi pretty much have got their Coke machines and Pepsi machines everywhere set up for credit card transactions and stuff like that. But as IoT becomes more prevalent, which remember, IoT or the Internet of Things really is the underlying foundation of just about everything we do. It drives automated transportation. It drives smart grid. It drives public safety. It pretty much drives everything. So as IoT expands, it keeps expanding, keeps growing. The concept of buying a SIM or buying another card, another interface, another service from a service provider doesn't make sense. So with 4G initially, and now more so with 5G, you have the ability to basically build out your own network and really do what the service providers are doing. Now, again, in terms of research and testing, that is very, very, very powerful. Because now not only can we really basically deal with the devices on the end and deal with the data, but we also have the ability to manipulate the attributes of the network. And you'll see in a few minutes here why that's important. So what's happened between 4G and 5G? Peak data rates in 4G, pretty much theoretically, you would max out at 1 gig. 5G, under 5G new radio, you have the ability to go up to 20 gig per user device. Data rates in megs per second, realistically, sustained, again, 10 meg with 4G and 100 meg with 5G. Latency has been cut way down from anywhere from 10 to 100 milliseconds to 1 millisecond. The latency part is not as important to things such as digital twin, but to things like smart grid and network control and stuff like that. Being able to control processes and systems, especially when you get into autonomous vehicles, the 1 millisecond latency becomes very, very, very critical. Mobility, the ability to transfer cell sites and stuff like that, that's gone from 350 kilometers to 500 kilometers an hour. Unless you own a Bugatti and a cell phone, it's probably not going to make much of a difference there. The next one is really, really, really critical. So with 4G, on a single network, you pretty much had the address space to be able to address about 100,000 units, 100,000 IoT devices. Now that's been brought up to 1 million. So it's gone up again an order of magnitude. The spectral efficiency in terms of how much bandwidth I can get, how much throughput I can get on the amount of spectrum that I've got has gone up threefold. Area capacity has gone up significantly, and energy efficiency has had anywhere approximately a 100-fold increase. So you can see going from 4G to 5G, we got more efficient, we got faster, we got more dense. We made a large number of changes. And all that now leads to the ability to be able to support the types of IoT that ultimately could end up leading towards the creation of the digital twins. Usage scenarios, what the 3GPP envisions here is that if you look at the spectral efficiency, that's really important for enhanced mobile broadband. What the mobility and the latency really help us in ultra reliable, and then massive machine really is really impacted by other aspects of 5G. So the massive machine is really what we would be focusing on in the digital twin arena. So people, whenever they talk about 5G and think about 5G, all they really think about is faster. That seems to be the one trigger point that everybody seems to really focus on. So EMBB, that's basically what the faster data rate is. That's where the broadband data and video comes in. That's the aspect of 5G that's important to that. The URLLC, that basically is the mission critical part of it, but that's ultra reliable network. So in essence, how do I make sure that the network is up and operating, especially if you're going to use a digital twin for operational processes such as simulation involved and large disasters and things like that. And then MMTC, the massive MIMO, that one there basically is the Internet of Things. That's again the one that really benefits us the most. So the way that all of these things were accomplished is the 5G architecture has been converted into a number of virtualized service-based architectures. So in essence, really basically, it's all Kubernetes that are sitting out there in a server somewhere. That gives us the ability to locate them, immediately adjacent to the architecture, and that's basically what we do when we're doing things like edge cloud. So instead of bringing, for example, if I'm doing analytics, doing facial recognition, instead of taking the facial recognition all the way back to the cloud, I have the ability to go ahead and put servers right at the cell nodes, and the edge cloud then basically becomes my computational capability. And that's in essence, that was established by going ahead and virtualizing all of the functionality within the architecture. Not only the mobile, not only the user plane, but also the control plane services of it. It also gives you the ability to create a resilient network. So in other words, I've got the network up and running, and it's running on some Kubernetes or some Dockers and a couple of machines. If one of them go down through things like VMware and other capabilities like that, I have the ability to automatically or in parallel run other virtualized functions to where I can go ahead and maintain that service and operate that service not round the clock without fear of interruption. So overall, basically, the flexibility of deployment options means greater ability support emergency communications incident. It also really does the exact same thing for the digital twin. Multi-edge access control. The reality is, if I'm going back to the cloud to do my analytics and do my work, I'm dealing with latency of up to 100 milliseconds, which again, if I'm just doing a simulation, really will not end up mattering a lot. But if I'm actually doing control, then that really makes a significant difference. You can see here now what's happened though, is they basically, you see up on the top one, the compute is over at the data center. There you're going across the internet. So you're adding in, you can't get around the speed of light and fiber. I mean, that's a law of physics. You can't really do any better than that. But if I go ahead and bring the compute right to my user plane, right to my user device, in essence, really I've eliminated not only the internet access, but I've also eliminated all of the fiber and transport that gets to that network. So again, reduces latency, reduces backhaul load. So I'm not putting everything out to the network. I'm not sending data over to the cloud just to do the computations to bring it back again to the user. Doing this improves reliability, deployability, and it's ideal for data intensive and latency sensitive applications. One of the other things that's come about in 5G is the whole concept of network slicing. So there's a few different components, elements in a 5G network. You got the core, which is the central part of it. That's the smarts of the network, and it really does all the signaling and controlling. You've got the transport that connects the core to the RAN, or the radio access network. And then you've got the RAN. The RAN is all the cell sites that are out there. In 4G, everything was basically in one common user plane, and everyone shared that user plane. So your public safety, your banking, your law enforcement, all of your information ended up sharing the same network. So you had to use virtualized services or VPNs on top of that to really go ahead and manage your security. Under 5G architecture, they've brought in the concept of network slicing. And the important part of that is each slice can have different parameters. So I can create, remember we were talking about the MMTC, the part of it that did the massive IoT. Well, I can create a slice that the network is tuned for that slice. If I have ultra reliable services, I create a slice for that slice. And if I have just high bandwidth, I create a slice for that. In the past, we had to take the entire network and optimize it for a compromise. So all aspects or all components of the network were basically, it was a compromise across the requirements of those 4 types of applications. Now it's set up to where, in essence, you can treat and manage each slice independently. Okay, so 5G enhancements that are going to benefit the digital twin. First of all, the FCC added, for the first time ever, shared spectrum. In the past, the service providers would buy the spectrum and use the spectrum, and it was licensed exclusively to them. If you were not an AT&T or Verizon or T-Mobile, you really didn't have spectrum. Now what they've done is they've set it up in a shared mode to where, in essence, things like CBRS, which is new spectrum that the FCC opened up, you can build your own network using open spectrum that lets you manage it as an entity, as opposed to having to go to the service providers to do it. There are now cloud and open source options. So a number of people have gone ahead and in some of the labs have built out basically an open source core, open source RAN, and done that on pretty inexpensive hardware, looking at servers that are in several thousands versus tens of millions of dollars to do. They've opened up the RAN option, the RAN systems now with ORAN. What that's doing is pushing towards open cell site architectures that are going to, as they really emerge, be a lot more cost effective, be a lot more efficient, and actually be able to be used by the enterprise, which universities are. Edge cloud, we've already talked about. IoT, I think we've talked about. The virtualization, we've talked about. Whoops, made a mistake in there. You can do it yourself. So in essence, the reality now is with 5G, you have the ability to build your own network. You have the ability to devise the capabilities and services that you need. This is exactly what we do at the iTech. We basically have got a lab that's built out that enables us to go ahead and support testing and research. We are an interdisciplinary function center. We've worked with several of the people that are on this in this workshop today, and we look forward to working with the rest of you going forward. And I have my contact info on the last slide.
Thank you, Walt.
How did I do for time, sir?
Yeah, that's great. We have